In section 10.2, we look at the way in which intermolecular forces affect the properties of liquids. And so just a little reminder about some of the characteristics of a liquid. The particles that make up a liquid tend to be organized randomly, but they are close together. So this is different from, say, in a solid, which we'll look at later on in the chapter, where the particles are organized in a very orderly manner, or a gas, where the particles are well separated from each other. So because particles are touching in a liquid, intermolecular forces play an important role in determining many of their properties. So some of the things that we'll be looking at in this section is why is it that liquid water is more dense than solid water? Why is it that some liquids have high boiling points and other liquids low boiling points? How come oxygen can dissolve in liquid water, which maintains the ecosystem in our oceans and also ecosystems in lakes and rivers? And how can water make it to the very top of a tree, even if a tree has no moving heart? So the first property of liquids that we'll look at is surface tension. And surface tension is the energy required to generate surface area. And it's actually energy per meter squared. So why does it cost energy to make surface? Well, in order to bring a particle from the bulk of a liquid to the surface, you have to break a bunch of intermolecular forces. And so as a result, that costs you energy because bond breaking is always an energy in process. Now, water has fairly high surface tension, and that's a direct result of the strength of the hydrogen bonds between its molecules. Because many liquids have surface tension, liquids tend to form shapes that minimize their surface area. So here you can see what they call the lotus leaf effect, where we have a drop of water sitting on a lotus leaf and it's curling into a sphere to minimize its surface area because forming surface costs energy. You can see this when water drips from a tap. It comes out as a sphere, and then as it falls, it ends up getting elongated due to the effect of gravity. Now, because of these intermolecular forces that create surface tension, that result in the creation of surface tension being an energy-intensive process, liquids with high surface tension will behave as what we call an elastic sheet. And if the intermolecular forces are strong enough, then you can float something like a needle well, this is commonly done with floating a needle on an oil when we make a compass. But you can float an object on a liquid, and water striders take advantage of the relatively high surface area of water to glide across water. So you've probably observed in the lab that when we put an aqueous solution in a glass tube, that it has a concave meniscus. That is, it kind of curves downwards, right? And why is that happening? Well, you have to think about the different forces that are acting on the water molecules, particularly those that are in contact with the walls of our tube. So firstly, there are what we call cohesive forces that are between the water molecules, and then there are adhesive forces between the water molecules and the glass walls of our container. Now, it turns out that the water molecules have stronger attraction to the glass wall of the container because it's got these very polar silicon-oxygen-silicon groups on the surface of the glass than what they have towards themselves. And so as a result, you see the liquid gets pulled a little bit up the walls of the container where it comes into contact with the container. Now, In mercury, when we put it in a glass tube, we see the oppositely shaped meniscus. We see a convex meniscus. And this is because the stronger metallic bonds, the intermolecular forces that are present in liquid mercury, are stronger than the attraction towards the glass walls of the container. So as a result, it pulls inwards towards itself. So one of the things that you should be able to comment on is, why does a liquid have either a concave or a convex meniscus when it's put into a glass container? And these kind of two examples illustrate that. So one of the things that you may have noticed is that if a tube containing an aqueous solution is narrow and it has relatively strong adhesive forces between the container walls and the liquid, then you can get a significant rise of the liquid up the tube. And you may or may not have seen that. And this is the same phenomena that rock climbers use when they climb up what's often referred to as a chimney, where you're just kind of relying on adhesive forces between yourself and the walls, and you can rise up the tube as high as you want to pretty effortlessly. Little kids are often able to do this, where you can kind of like wedge yourself into a doorway like this. Most adults can't, because they can't create enough attractive force using outward pressure to support their weight. But you might have memories of doing that when you were a kid. So with this sort of what is often referred to as capillary rise, the narrower the tube, the more pronounced the effect. And in plants, they have lots of little narrow tubes, and they're lined with cellulose, which is highly attractive to water molecules. And so liquid can rise a considerable amount, and this is referred to as capillary action. And that's how plants and other organisms that don't have a heart that pumps can move liquid around. So one of the other properties of liquids that's dependent on intermolecular forces is viscosity. And viscosity is just resistance to flow. And basically, the thicker and more honey-like a liquid is, the greater its viscosity. And so what is going to determine the viscosity of a liquid? Well, for nonpolar molecules, where the only intermolecular forces are dispersion forces, viscosity is going to increase with molecular weight. So chemical engineers that are attempting to increase the viscosity of a liquid for a particular application, they'll know that a simple way of doing that is just to make the molecule bigger. Now, if you have a polar molecule, or a polar liquid in particular, then we need to consider both molecular weight, which is going to largely determine dispersion forces, and also how polar the molecule is. So viscosity is often measured using these what are called centipoise units. That's what this CP stands for. And here we can see how the viscosity of these polar molecules is determined not just by the molecular weight, but also how the presence of polar groups as well. So each of these molecules have a polar OH group, which can hydrogen bond, and then the molecular weight is being manipulated by adding a longer and longer hydrocarbon chain. So as the hydrocarbon chain grows longer, we can see that the viscosity increases, right? So that's what's happening there. So you can see that it's a balance of the forces, and they all have close to the same sort of sized polar region, but they have increasing dispersion forces as we increase the molecular weight with the increasing hydrocarbon chain length. Now, for most liquids, density will increase with decreasing temperature. And this is also true for liquid water to a certain point, until we get to 4 degrees Celsius. So here we are at 10 degrees, we decrease the temperature, and sure enough, what happens? The density goes up but once we hit 4 degrees, as we continue to decrease the density, decrease the temperature, the density starts heading down. So that's kind of interesting, isn't it? And it'll be nice to know why that is. Once we get to the freezing point, you can see that the density of the water is actually less than 1, which is what the density of water is at room temperature. So that's kind of interesting. All right. So this increased density of liquid water between 0 and 4 degrees Celsius has a few kind of interesting consequences. One of them is that what happens as we cool below, as we cool down to 4 degrees Celsius, the water tends to become more dense and sinks, but then once we cool past 4 degrees Celsius, it becomes less dense and rises. And so what this means is that in the autumn, we get this kind of like turnover. It's called the autumnal turnover. And what it does is it brings nutrients from the bottom of lakes and rivers and things up to the surface, and it replenishes the water. So that's kind of cool, right? The other thing that happens is that once we get to the freezing point of water, the density drops even further, and ice has a density of about 0.92 grams per milliliter, which makes it less dense than liquid water, which has a density of around about 1 gram per milliliter. So what that means is that ice floats on liquid water, and you probably noticed this because the ice cubes float in your drink, and also there's a thing called icebergs, right? So why does this happen? That's an interesting question, isn't it? Why is solid ice less dense than liquid water? Well, the reason is hydrogen bonding. If every water molecule in ice maximizes its hydrogen bonding capacity, then each water molecule will form 4 hydrogen bonds, and those hydrogen bonds will be oriented in a tetrahedral fashion. And what this gives rise to is a structure that has hexagonal channels through it. It ends up having large open spaces in the structure. So when the water cools and the molecules begin to crystallize and align themselves to maximize hydrogen bonding, well, you end up with a relatively open structure, and as a result, ice floats on liquid water. Now, the lower density of ice compared to liquid water, it has a couple of interesting consequences. One is that it creates a habitat for creatures like seals and penguins and polar bears and stuff that love to live on sea ice. And the other thing that happens is that the ecosystem can continue to function underneath the ice. So if the ocean was to freeze from the bottom up, then the entire bottom of the ocean would get sterilized, and all the plants in the ocean would die, and we would have a very we'd have a big problem. The ocean just would cease to function every winter. The other important role that sea ice plays is that it helps modulate our climate because, well, sea ice is white, and so what that means is that when solar radiation hits it, it is reflected rather than absorbed, and so some of the energy that hits our planet from the sun gets reflected back out into space rather than being absorbed by the ocean. So it helps keep our planet a little cooler than it would be if there was no sea ice. Okay, so that concludes the video for section 10.2.